The B-17 flying fortress designated Lucky Strike wasn't flying anymore. It was falling with style, held aloft by nothing but physics that had stopped making sense about 20 minutes ago. The number 3 engine wasn't just dead, it was gone. Ripped clean off the wing by German 88mm flak over Bremen, leaving a gaping wound that screamed into the freezing air at 180 miles per hour. Hydraulic fluid painted crimson streaks along the olive-drab fuselage, and if you didn't know better, you'd swear the plane was bleeding out. The ball turret gunner was already gone, lost somewhere over the target. The turret itself hung at an angle that made veteran mechanics wince when they saw the photos later. Inside the fuselage, 8 men were doing everything they could to keep a dying aircraft in the air long enough to see England again. Pilot Lieutenant Marcus Webb had both hands locked on the yoke, fighting control surfaces that barely responded, coaxing a plane that weighed 65,000 pounds to do something it had no business doing, staying airborne. By every manual, every regulation, every engineering specification Boeing had ever published, this bomber should have augured into the North Sea within minutes of taking that flak hit. The math didn't work, the physics didn't work. Nothing about this situation worked, except it did. When Lucky Strike finally kissed the runway at RAF Bassingbourn, it did so on one landing gear leg. The other had refused to deploy because, technically speaking, there was no hydraulic pressure left in the system to deploy it. Webb brought that crippled fortress down on one wheel and a prayer, skidding sideways down the tarmac in a shower of sparks visible from the control tower a mile away. The crash crews sprinted toward the wreckage, expecting to pull out bodies, maybe 1 or 2 survivors if they were lucky. Instead, they found 8 men climbing out under their own power, shaken, definitely, in shock, absolutely, but alive and walking. The 9th man, that ball turret gunner, was already being mourned. But 8 out of 10 crew members walking away from a plane that looked like it had been through a metal shredder. That wasn't supposed to happen. That wasn't supposed to be possible. Group Commander Colonel James Albertson stood on that tarmac as the winter sun set over England, staring at the smoking wreckage of Lucky Strike, and asked the only question that mattered. How? How did a plane with no hydraulic pressure, catastrophic fuel system damage, and electrical failures that should have made controlled flight impossible manage to not just stay in the air, but land successfully? How did 8 men walk away from damage that, according to every after-action report from the past year, should have killed all of them? The official answer would take months to emerge through proper channels, investigation reports, and engineering analysis. But the real answer was already working in a hangar 200 yards away, elbow deep in another B-17's engine cowling, making modifications that would have gotten him court-martialed if anyone in authority had bothered to document what he was actually doing. See, the Army Air Forces in late 1943 had a problem they couldn't quite articulate in the official reports. Bombers were going down. That part was expected. This was war over Nazi Germany, and the Luftwaffe wasn't known for their hospitality. But something else was happening, something that kept showing up in the loss statistics, if you knew how to read between the lines. Planes were going down from damage that shouldn't have been fatal. A B-17 could supposedly absorb punishment that would shred 3 fighter planes. That was the whole point of the name Flying Fortress. These machines were built to take hits and keep flying. Early combat reports from 1942 made it seem like you could fly a fortress through a brick wall and it would come out the other side asking for more. Crews had nicknamed them the plane that wouldn't die, but by late 1943, experienced crews were noticing a disturbing pattern. A single flak burst in the wrong spot, and a bomber worth $200,000 and carrying 10 highly trained airmen would simply fall out of formation and disappear. Not from concentrated fighter attacks, not from direct hits to engines or control surfaces, from one piece of shrapnel hitting one specific spot, and suddenly nothing worked. The math was brutal. The 8th Air Force was losing bombers at a rate of approximately 5% per mission by autumn 1943. Crew tours required 25 missions. Do that math and you realize that a crew's odds of completing their tour were essentially a coin flip. 50-50. Survive or don't. And the thing that was killing them wasn't always overwhelming enemy fire. Sometimes it was their own airplane giving up from damage that looked survivable. Something fundamental was wrong with the design, but Boeing wasn't about to admit that their flagship bomber had a critical flaw. The Pentagon wasn't interested in hearing complaints when production lines were running at full capacity, and crews kept dying because nobody wanted to acknowledge that the plane they'd all been told was indestructible had an Achilles heel you could drive a truck through. Lucky Strike's survival wasn't luck. It was proof that someone had figured out what was wrong and fixed it, using methods that would make procurement officers spontaneously combust. This is the story of how one mechanic's unauthorized, technically illegal, completely forbidden modifications turned the B-17 from a statistical death sentence on certain missions into the legendary survivor it's remembered as today. And it started with a guy who'd learned to fix things not in any Army technical school, but in a Depression-era garage in Pittsburgh, where the operating principle was brutally simple. Make it work, or it doesn't get fixed. There were no backup parts. There was no supply depot. There was just your brain, your tools, and whatever scrap metal you could scrounge. That mindset, forged in poverty and necessity, was about to save thousands of lives. Staff Sergeant Paul Zuk wasn't supposed to be fixing airplanes. According to his Army Air Force's personnel file, he'd scored high enough on mechanical aptitude tests to warrant assignment to the motor pool. Trucks, jeeps, the unglamorous machinery that kept an airbase running but never got you mentioned in combat reports. It was safe work, relatively speaking. You didn't get shot at while changing oil in a deuce and a half, but someone in the personnel office at RAF Bassingbourn had actually read his file instead of just rubber-stamping assignments. They'd seen his civilian work history and made a lateral transfer that probably saved 100 lives, though nobody would ever calculate it that precisely. Before the war, before the draft notice arrived at his apartment in Pittsburgh's Polish Hill neighborhood, Paul Zuk had run a repair shop that survived on one principle: fix anything for anyone who could pay. That often meant fixing things for people who couldn't pay much, which meant improvising solutions with whatever parts you could afford or scavenge. Coal trucks with engines held together by creative welding. Delivery vans running on parts cannibalized from 3 different manufacturers. The occasional bootleggers souped up Ford that needed to outrun police but couldn't afford factory performance parts. Zuk kept them all running on budgets that would make a poverty line look generous. He arrived at Bassingbourn in August 1943, 26 years old, with grease already permanently embedded under his fingernails and an attitude about regulations that his commanding officers would alternately find infuriating and invaluable. He had that look common to men who'd grown up during the Depression, lean-weathered with eyes that sized up problems with the cold calculation of someone who'd learned early that resources were finite and failure meant going hungry. His first week on the flight line, Zuk watched a crew chief reject a B-17 for a cracked hydraulic line. Standard procedure, completely by the book, absolutely correct according to Technical Order 0120EG2, the Bible of B-17 maintenance. The replacement part was on back order. Nobody knew when it would arrive. Could be 3 days, could be 3 weeks. The plane sat grounded. The mission went out 1 bomber short. The group flew at reduced strength because one hydraulic line, just one, had a crack in it. Zuk studied the damaged line for maybe 30 seconds. Then he asked the crew chief a question that probably sounded naive to someone who'd learned maintenance by the Army's book. Why can't we bypass the damaged section and reroute through the secondary line? The crew chief, a lifer who'd been in the Army since before Pearl Harbor, looked at Zuk like he'd suggested using baling wire to attach the wings. "That's not in the manual, Sergeant." Zuk's response, delivered in a Pittsburgh accent thick enough to cut with a wrench, became legendary in the maintenance section. It got repeated in hangars across England, usually with the accent imitated badly. The manual didn't grow up fixing trucks during the Depression. I did. That response encapsulated everything about Paul Zuk that would matter over the next year. He hadn't learned maintenance from textbooks or technical schools. He'd learned it from necessity, from reality, from the brutal education of fixing things that absolutely had to work because there was no other option. Here's what made Zuk fundamentally different from the mechanics who'd learned their trade in Army technical schools. Those guys were good at their jobs. They could follow a technical order perfectly, execute repairs exactly as Boeing engineers had specified, and maintain a B-17 to factory specifications with precision and skill. But Zuk could look at a system that was failing and ask a question the engineers apparently hadn't considered. What happens when this breaks over Germany at 25,000 feet, and there's no parts depot, no supply chain, no backup, nothing but 10 men who need this plane to keep flying for another 3 hours or they die? His genius wasn't in understanding how things were supposed to work. Every mechanic understood that. His genius was in understanding how things could still work when everything went wrong. How you could keep critical systems functioning after they'd been hit, damaged, or degraded. How you could build in redundancy and backup pathways that would let a crew limp home instead of ditching in the North Sea. By October, other mechanics had started noticing something odd. Planes that Zuk serviced had a weird habit of coming back from missions they shouldn't have survived. A bomber he'd worked on took flak through the hydraulic bay, should have lost all landing gear control, but the pilot managed a wheels-down landing. Another bird lost primary electrical after a fighter attack, yet somehow the instruments kept working long enough to get the navigator home. Lucky coincidence, the crew chief said. Zuk didn't believe in luck. He believed in redundancy. He believed in backup systems. He believed in routing critical functions through pathways that weren't in the Boeing blueprints, because Boeing had apparently never considered what happened when their beautiful, efficient single point of failure designs met German 88mm flak over industrial targets. While other mechanics replaced parts according to the technical orders, Zuk was redesigning systems on the fly, using scavenged components from damaged aircraft in the salvage yard, borrowing tubing and electrical wire from a dozen different sources, creating jury-rigged connections that would have made an inspector from Boeing weep with horror, but worked when the factory design failed. The other mechanics started calling him the plumber, because he was always rerouting something. Hydraulic lines, fuel feeds, electrical bundles. He'd spend hours after official duty hours ended, alone in the hangars with just a flashlight clenched between his teeth, rewiring planes in ways that never appeared on the maintenance logs. Because technically, what he was doing violated about 15 different Army regulations. Unauthorized modification of combat aircraft, use of non-standard parts, deviation from approved technical procedures. Each violation carried potential court-martial charges. Each violation could end his military career and possibly land him in Leavenworth. When asked why he bothered, given that he could have sat in the motor pool drinking coffee and avoiding trouble, Zuk's answer was characteristically blunt. Those guys fly the missions. Least I can do is make sure the plane doesn't kill them on the way home. The B-17 Flying Fortress was supposed to be indestructible. Boeing's marketing materials practically said so in bold print. The early combat reports from 1942 seemed to confirm it. Fortresses came back from missions looking like flying cheese graters, holes punched through wings, fuselage, tail surfaces, yet they kept flying. Crews swapped stories in the officers' club about planes that absorbed hundreds of hits and still made it home. There was the famous photograph of a B-17 that had collided with a German fighter. The fighter's entire tail section had been sheared off, embedding itself in the fortress's fuselage. The bomber flew home like that, landed successfully, and the crew walked away. If that wasn't proof of invincibility, what was? But by late 1943, a disturbing pattern was emerging in the loss statistics that nobody wanted to discuss openly. Planes weren't just getting shot down by overwhelming force, they were going down from single points of failure, one hit in the wrong spot, and a bomber worth $200,000, and 10 trained crew members would spiral out of formation and disappear. The 8th Air Force was losing approximately 5% of bombers per mission by autumn 1943. Some missions were worse. The second Schweinfurt raid in October 1943 saw a loss rate of 20%. 60 bombers gone in one day, 600 men killed, captured, or missing. Something was killing B-17s that shouldn't have been fatal. And it took mechanics like Zuk actually examining the wreckage, talking to surviving crews, and piecing together the pattern to figure out what the problem was. Hydraulics. The B-17's hydraulic system controlled everything that mattered when you were trying to not die. Landing gear, brakes, wing flaps that let you control airspeed. And most critically, the turret systems that allowed gunners to track attacking fighters. Without hydraulics, a B-17 was just a very expensive glider with no way to land safely. Boeing had designed an efficient system. Primary hydraulic lines ran through the fuselage in tidy bundles, grouped together because that's what you do when you're designing for peacetime manufacturing efficiency. Keep everything organized. Route systems together, minimize production time, reduce costs. But efficient meant concentrated. All your eggs in one basket. One piece of flak through the wrong 6 inches of fuselage, and you lost hydraulic pressure to multiple critical systems simultaneously. Suddenly, you couldn't control your landing gear, couldn't adjust your flaps, couldn't traverse your gun turrets. A bomber could have 3 functioning engines, intact wings, a healthy crew, but without hydraulics, you were looking at a belly landing on an English runway. And belly landings in B-17s had an unpleasant tendency to turn into fireballs when fuel tanks ruptured on impact. Then there was the fuel system, which had its own creative ways of killing people. The B-17 carried 2,580 gallons of 100-octane aviation fuel distributed across 9 separate tanks, 5 in the wings, 4 in the fuselage. The feed system was brilliantly designed. Fuel flowed from the outer wing tanks inward, maintaining balance automatically as fuel was consumed. The system worked flawlessly under ideal conditions. But combat over Germany in 1943 wasn't ideal conditions. The fuel lines connecting those tanks ran through areas that were absolutely in the firing cone when German fighters made beam attacks from 3 o'clock or 9 o'clock positions. A single 20mm cannon round through a fuel line didn't just mean you lost fuel, though you certainly did, catastrophically fast. It meant you now had aviation gasoline spraying inside an airframe, where hot metal from the hit electrical sparks from damaged wiring and the simple act of flying through sub-zero air at 25,000 feet created perfect conditions for either immediate fire or vapor lock. Zuk had noticed something the official engineering reports hadn't caught. Planes that went down with unknown causes, listed in after-action reports, often showed pre-impact fuel system anomalies in their final minutes. Pilots would report rough engines, then one engine would quit, then another. Then the whole plane would start shaking itself apart or suddenly burst into flame for no apparent reason. Post-crash analysis, when there was anything left to analyze, kept using phrases like fuel contamination or air in the lines, without explaining how that happened. What was happening was devastatingly simple once you understood it. Flak or fighter fire would damage a fuel line somewhere in the system. Air would get sucked into the lines through the damage. That air would travel through the fuel system like a poison, creating pockets that disrupted fuel flow. Engines would start running rough because they were getting fuel mixed with air instead of pure fuel. They'd lose power. Then they'd quit entirely. And the bomber would go down, not because it was too damaged to fly, but because it was choking itself to death on its own compromised fuel system. The airframe would be intact. The crew would be alive. But the plane would be unflyable because the fuel system had cascaded into failure from one single point of damage. Boeing's engineers had built an airplane that worked beautifully when everything was perfect. But combat over Germany in 1943 was the opposite of perfect. It was chaos. It was metal flying at supersonic speeds through the airspace you occupied. It was explosions that turned aircraft aluminum into shrapnel. It was an environment where every system needed to assume it would be damaged and had to keep working anyway. The B-17's Achilles heel wasn't lack of armor. It wasn't insufficient firepower. It was single point of failure design philosophy embedded into critical systems. One hit in the wrong place and everything stopped working because everything was connected to everything else in ways that made failure cascade through the entire aircraft. And that's what Paul Zuk started fixing. One unauthorized modification at a time, working alone in hangars after dark, using parts that weren't in any supply system, creating backup systems that weren't in any manual. He was saving lives using methods that could get him court-martialed, but the alternative was watching crews die, because nobody else would break the rules to fix a broken design. What Zuk did wasn't technically illegal. It was worse than that. It was unauthorized field modification of combat aircraft systems, which meant if a plane crashed and investigators traced the failure back to his modifications, he'd be facing court-martial charges for negligent homicide, possibly manslaughter. Certainly enough to put him in military prison for years. The Army took unauthorized modifications seriously for good reasons. Aircraft were complex machines where every system interacted with every other system in ways that weren't always obvious. Change one thing without understanding the downstream effects, and you could create failures that killed people. The regulations existed to prevent well-meaning mechanics from inadvertently turning aircraft into death traps, but Zuk had done his own math, and his calculations were brutally simple. If he did nothing, planes crashed anyway. Crews died anyway. The official systems were failing in combat, and the official response was to keep following the same procedures that weren't working. At least, if he tried something different, crews had a chance. The core of his forbidden fix was elegant in its simplicity. Create redundancy where Boeing hadn't bothered. Take that hydraulic system with its neat, efficient, single-bundle design and turn it into a chaotic mess of backup lines that looked like a plumber's nightmare, but functioned when the primary system took a hit and died. Zuk started scavenging hydraulic tubing from damaged aircraft, sitting in the salvage yard at the edge of the base. Stuff that was technically supposed to be catalogued, documented, and sent back through official channels for recycling. He'd identify sections of undamaged tubing, cut them carefully, test them for pressure integrity using a hand pump he'd jury-rigged from spare parts, and then smuggle them back to the main hangars hidden under toolboxes and equipment. Here's how his modification worked in practice. Our standard B-17 had one main hydraulic line running from the hydraulic pump located near the cockpit, back to the landing gear actuators in the rear fuselage. Elegant, efficient, simple, and fatally vulnerable. Zuk would tap into that main line at 2 points, one forward near the cockpit bulkhead, one aft near the radio compartment. Then he'd run a secondary hydraulic line along a completely different path through the fuselage, usually tucked along the structural stringers, where it was partially protected by the aircraft's framework. The backup line followed a route that minimized exposure to the same areas the primary line traversed. Then came the clever part. At each junction point where the backup line tapped into the primary system, Zuk installed manual isolation valves. These weren't standard B-17 parts. They were valves cannibalized from damaged bombers, modified to fit, and installed in positions where the pilot or co-pilot could reach them without leaving their seat. If the primary hydraulic line took a hit and lost pressure, the pilot could reach down. Zuk always mounted the valves within arm's reach of the pilot's seat and manually rotate the isolation valves. This would close off the damaged primary line and open the backup line. Hydraulic fluid would start flowing through the secondary system. Pressure would build. Landing gear, brakes, and flaps would function again. It wasn't elegant. It added about 60 pounds of weight to the aircraft. It violated Technical Order 01-20EG-2 Section 4, Paragraph 12, Subsection C, which explicitly prohibited unauthorized hydraulic system modifications, and it meant the difference between landing on wheels or skidding down the runway on the belly, praying the fuel tanks didn't rupture and turn the landing into an inferno. The fuel system fix was even more radical. Zuk couldn't prevent fuel lines from getting hit. That was simply a fact of flying through flak barrages. But he could prevent a single hit from cascading into complete system failure that would choke the engines and kill the plane. He started installing crossover valves between separate tank systems. These weren't unauthorized parts, technically. They were standard fuel petcocks designed for ground refueling operations, but Zuk installed them in positions where the flight engineer could access them during flight, with clear labeling showing which valve controlled which tank. Now, when a fuel line took damage, and air started contaminating the system, the flight engineer could isolate the compromised tank by closing its feed valve. Then he could manually open crossover valves to reroute fuel from intact tanks directly to the engines that needed it. Instead of the automatic system trying to balance fuel draw from all tanks and failing because one system was compromised, you could manually tell the plane, use these specific tanks, ignore that damaged one. The documentation on these modifications was deliberately vague. Zuk would write them up in maintenance logs as refueling system check valves installed and tested. Technically accurate, deliberately misleading. The inspection officers who spot-checked maintenance logs saw standard terminology and assumed standard work. But the modification that really saved lives, the one that kept crews from flying blind into German airspace, involved the electrical system. B-17s had a primary electrical bus that powered everything from flight instruments to gun turret motors to radio equipment. The system was powered by two main generators, one on each inboard engine. Power flowed through the main bus to distribution points throughout the aircraft. One hit to that primary bus and you were flying dark. No instruments to tell you altitude or airspeed. No radio to coordinate with other aircraft or call for help. No powered gun turrets because the traverse motors needed electricity. You became a blind, deaf bomber waiting to be picked off by fighters who could see you just fine. Zuk started running secondary power lines from the auxiliary generator directly to critical systems, bypassing the main electrical bus entirely. He'd hide these emergency lines inside existing cable bundles so they looked like factory wiring until you actually traced where they originated and where they terminated. He used different colored insulation, bright yellow instead of the standard black, so pilots and crew would immediately recognize which circuit breakers controlled the emergency backup systems. The result was that even if the main electrical bus got hit and died, the most critical systems would keep functioning. Basic flight instruments, radio, at least one gun turret position. Not everything would work, but enough would work to give the crew a fighting chance to get home. The brilliance of Zuk's approach wasn't that he invented new technology or designed revolutionary systems. Everything he used was already on the aircraft or sitting in parts bins waiting to be installed somewhere. He was just rearranging the pieces in ways Boeing's engineers hadn't considered. Boeing had optimized their design for manufacturing efficiency, for production speed, for cost control. They'd built an aircraft that could be assembled quickly by workers who'd been civilians 6 months earlier. Many of them women who'd never seen the inside of a factory before the war. Zuk's modifications required a skilled mechanic who understood systems theory, who could visualize how fluids and electricity flowed through complex pathways, and who wasn't afraid to deviate from the blueprint when the blueprint was getting people killed. By January 1944, Zuk had quietly modified 17 B-17s in the 351st Bomb Group. He never advertised what he was doing. He just did the work during night maintenance shifts when fewer officers were around to ask uncomfortable questions about why he was installing hydraulic lines that weren't on any work order. And those 17 bombers were coming home from missions at a rate that was starting to look statistically impossible. Other mechanics noticed. Crews noticed. And eventually, someone in authority was going to notice. And then Paul Zuk's unauthorized engineering revolution was going to face its biggest test, official scrutiny. February 8, 1944, 0930 hours. Captain Ronald Fletcher, the engineering officer for the 351st Bomb Group, was having what would charitably be described as a very bad morning that was about to get exponentially worse. Fletcher was conducting routine maintenance inspections, the kind where you randomly pull aircraft from the flight line and verify they match their technical documentation. The kind of inspection where you hope to find nothing because nothing meant everything was running according to regulations. He'd selected a B-17 called Devil's Daughter for spot inspection purely at random, opened the hydraulic access panel in the forward fuselage to verify the system matched the maintenance logs, and found plumbing that absolutely should not exist. Fletcher had been an aeronautical engineering student at MIT before the war interrupted his education. He'd studied aircraft design theory. He could read technical blueprints in his sleep. He knew what a factory-standard B-17 hydraulic system looked like. What he was looking at now wasn't on any Boeing blueprint he'd ever seen, secondary hydraulic lines running through non-standard routes along the fuselage stringers, manual isolation valves installed in positions that required custom bracketry, fuel crossover connections that used parts from what appeared to be 3 different aircraft types, electrical wiring in yellow insulation running parallel to standard black wiring but following different paths to different destinations, and all of it done with a level of craftsmanship that immediately told Fletcher this wasn't some sloppy field expedient repair. This was deliberate, thought-out modification. Someone had carefully planned these changes, fabricated custom parts, and installed everything with the precision of someone who knew exactly what they were doing, which made it worse, not better, because unauthorized modifications done competently were potentially more dangerous than crude hacks. They looked professional enough that other mechanics might not catch them. They might propagate to other aircraft. And if something went wrong, if one of these modified systems failed catastrophically, people would die, and nobody would understand why, because the modifications weren't documented anywhere official. Fletcher closed the access panel, made notes on his inspection clipboard, and went looking for the crew chief responsible for Devil's Daughter. He found Staff Sergeant Paul Zuk in Hangar 3, working on an engine swap. Zuk was shoulder-deep in an engine cowling, torquing bolts with the methodical precision of someone who'd done this particular job 1,000 times before. "Sergeant Zuk, we need to talk about Devil's Daughter's hydraulic system." Zuk didn't even look up from the cowling he was working on, didn't pause in his work, just kept torquing bolts with that steady rhythm. "What about it?" Fletcher pulled out his inspection clipboard, reviewing his notes to make sure he had the details right. "What about it? What about the fact that there are approximately 40 feet of unauthorized hydraulic line installed in non-standard routing configurations? What about the manually operated isolation valves that aren't specified in any technical order I've ever seen? What about the fuel crossover system that appears to use parts from at least 3 different aircraft types?" Zuk set down his torque wrench, wiped his hands on a rag that was somehow dirtier than his hands were, and gave Fletcher a look that was equal parts exhausted and defiant. The look of a man who'd been expecting this conversation eventually and had already decided how it would go. "You want the official answer or the real one, sir?" Fletcher's response was immediate. "Both. Starting with how long you've been doing this and how many aircraft are affected." 17 planes. Zuk said it matter-of-factly like he was reporting how many spark plugs he'd changed that week. 17. That number hit Fletcher like a physical blow. 17 aircraft in active combat service, with undocumented modifications to primary flight systems. The regulatory violation was staggering. This wasn't one mechanic making one questionable repair. This was a systematic, ongoing modification program that had been running under everyone's nose for months. Zuk could be court-martialed. Multiple charges: unauthorized modification of combat aircraft, dereliction of duty, potentially even sabotage if some prosecutor wanted to be creative. Fletcher himself could face disciplinary action for not catching this sooner, for not maintaining adequate oversight of maintenance operations. The career implications were cascading through Fletcher's mind at light speed. But then, almost despite himself, he asked a question that wasn't about regulations or procedures or covering his own ass. He asked the question that actually mattered. Have any of these 17 aircraft experienced hydraulic system failures? Zuk pulled out a grease-stained notebook from his coverall pocket, his personal maintenance log, the unofficial record he kept, because the official forms never had enough space to write down everything that mattered. He flipped through pages, filled with notes, written in cramped handwriting, dates and aircraft tail numbers, and technical observations documented with the obsessive precision of someone who actually cared about whether his work functioned. 3 of them took flak hits to primary hydraulic lines. All 3 made it home on the backup system. Devil's Daughter landed on her own gear 2 weeks ago after 88 minutes flak took out her primary line over Frankfurt. Pilot didn't even know he was flying on backup until I showed him the damage post-flight. He thought he'd just gotten lucky. Fletcher did the mental math. 3 catastrophic hydraulic hits. 3 aircraft that should have been unable to lower landing gear, that should have been forced into belly landings or ditching in the North Sea. 3 aircraft that made it home safely instead. The standard statistical model said at least 2 of those planes should have been written off as total losses. At least 2 crews should have been killed or seriously injured in crash landings. Fletcher stood there in Hangar 3, holding his inspection clipboard, aware that he was at a decision point that would define his military career and possibly affect hundreds of lives. By the book, he should report Zuk immediately. Formal investigation, court-martial proceedings, make an example of him to discourage other mechanics from conducting unauthorized modifications, maintain discipline and proper procedure. But 3 planes had made it home when they should have crashed. 3 crews were alive when they should have been dead. "I need to escalate this," Fletcher finally said, "but not the way you probably think." By noon, Fletcher had briefed Group Commander Colonel Albertson. By 1400 hours, Albertson himself was in Hangar 3 personally inspecting Zuk's modifications while Fletcher provided technical narration. And by 1600 hours, there was a very uncomfortable meeting happening in the Group Operations Office. The question on the table wasn't simple. It wasn't just about whether Paul Zuk had violated regulations. That much was obvious. The question was whether to court-martial him for it or give him a medal. Because the survival statistics were starting to tell a story that made everyone deeply uncomfortable. A story about how many crews might have died because the official systems hadn't been good enough. About how one mechanic with a high school education and Depression-era practical experience might have understood something that MIT-educated engineers had missed. The decision that came out of that meeting would set off a chain of events that would eventually change how the Army Air Forces thought about field modifications, combat survivability, and the difference between following procedures and actually solving problems. But in that moment, standing in Hangar 3 with his personal maintenance logs in hand, Paul Zuk didn't know any of that. He just knew he'd been caught doing something that could send him to prison. And the only defense he had was 17 planes that kept coming home when they shouldn't have. Sometimes that's enough. Major Henry Watkins from the 8th Air Force engineering staff arrived at Bassingbourn on February 10th with orders that were simultaneously vague and terrifying. Investigate unauthorized field modifications to B-17 aircraft and determine if they pose safety risks to flight operations. He spent 3 days living in the hangars, crawling through Zuk's modified aircraft with a flashlight and a camera, photographing every non-standard installation, reviewing maintenance logs, and interviewing pilots and crew members who'd flown the modified planes. Watkins was thorough because his career depended on it. If he gave these modifications a pass and one of them failed catastrophically, he'd be the one explaining to grieving families why he'd approved a mechanic's unauthorized hack job. But if he condemned the modifications and crews kept dying from hydraulic failures that could have been prevented, he'd spend the rest of his life knowing he'd chosen paperwork over people. His preliminary report, filed February 13th, contained a paragraph that probably took him several hours to write. Not because the engineering analysis was complex, but because he was essentially admitting that the Army Air Forces had been sending crews into combat with preventably vulnerable aircraft. The paragraph read, "While SSGT Zuk's modifications are unauthorized and violate standing technical orders, preliminary analysis suggests these changes address systemic vulnerabilities in hydraulic and fuel system design that may be contributing factors in combat losses currently attributed to enemy action. Recommend against punitive action, pending comprehensive engineering evaluation, and controlled testing of modified systems under combat conditions." That single paragraph saved Paul Zuk's career, but it also opened a door that nobody in the Pentagon particularly wanted opened. The door that led to uncomfortable questions about how many crews had died because Boeing's production-optimized design had prioritized manufacturing efficiency over combat survivability. Colonel Albertson made a command decision that probably bent several regulations itself. Zuk wouldn't face immediate charges, but he also couldn't modify any more aircraft until the engineering evaluation was complete. The 17 already modified bombers would continue flying missions because even the most regulation-bound brass could read survival statistics. And in the meantime, Major Watkins would come back with a team of engineers to determine once and for all whether Paul Zuk was a genius or a dangerous maverick who'd gotten lucky. Major Watkins returned to Bassingbourn on March 3, 1944, with 2 Boeing civilian engineers under military contract, a team of Army Air Forces technical specialists, and a mandate that essentially read, "Prove this works or prove it's dangerous, but do it fast because we're losing bombers over Germany at rates we can't sustain." What followed was probably the most unorthodox engineering validation program in military aviation history. Testing unauthorized field modifications under actual combat conditions while simultaneously trying to figure out if you should be documenting this as innovation or collecting evidence for criminal proceedings. The Boeing engineers were appalled at first sight. The lead engineer, a man named Robert Carlson, who'd worked on the original B-17 design back in Seattle, spent his first hour at Bassingbourn using phrases like pressure regulation concerns, potential contamination risks, and catastrophic failure modes waiting to happen. He stood in front of a partially disassembled Devil's Daughter, pointing at Zuk's bypass lines with barely contained horror, explaining to Watkins in precise engineering terminology why this couldn't possibly work according to established hydraulic systems theory. He talked about pressure drop calculations across non-standard line lengths, about the risks of cavitation in manually controlled valve systems, about filtration requirements that Zuk's scavenged components couldn't possibly meet. He had charts, he had equations, he had Boeing's internal testing data that proved these modifications violated fundamental design principles established by people with engineering degrees from prestigious universities. Zuk stood there in his grease-stained coveralls, letting Carlson finish his lecture. Didn't interrupt, didn't argue. Just listened with the patient expression of someone who'd heard similar pronouncements before and knew how they'd turn out. When Carlson finally wound down, Zuk asked a simple question. "When's the last time you flew a combat mission, sir?" Carlson bristled immediately. "I'm an engineer, Sergeant, not a pilot." Zuk nodded slowly. "Right. So you designed this system in Seattle, where the worst thing that happens during testing is a failed pressure test, and you get to try again tomorrow. I maintain these birds after they come back with holes in them. Different perspective on what failure means. The tension in that hangar was thick enough to cut. You had the MIT-educated engineer who'd helped design the B-17, and the Pittsburgh mechanic with a high school diploma who'd taken that design and changed it. Two completely different worldviews about to collide. Major Watkins, to his eternal credit, cut through the territorial posturing with a proposal that was either brilliant or insane. We instrument some of these modified aircraft with additional monitoring equipment, pressure gauges, flow meters, recording devices. Then we send them on actual combat missions while documenting exactly how these systems perform under real conditions. In any sane procurement process, this would require months of ground testing first, controlled environments, gradual validation, risk mitigation protocols. But this was March 1944. The air war over Germany was reaching a crescendo. The 8th Air Force was losing an average of 6 bombers per major mission. They didn't have months to run controlled tests. Between March 5th and March 18th, 5 of Zuk's modified B-17s flew a total of 11 combat missions to targets including Berlin, Brunswick, and Friedrichshafen. Each aircraft carried additional instrumentation that recorded hydraulic pressure in both primary and secondary systems, fuel flow rates from each tank, and electrical system performance throughout every phase of the mission. 3 of those 5 bombers took battle damage during those 11 missions. All 5 came home. The data was irrefutable, captured on strip chart recorders that couldn't lie or be manipulated. On the mission to Friedrichshafen on March 18th, the instrumentation recorded primary system pressure dropping from 1,500 psi to absolute zero in 4.2 seconds. Standard procedure said the aircraft should have been unable to control landing gear, flaps, or brakes from that moment forward. Memphis Belle II should have either attempted a belly landing or ditched in the English Channel. The crew should have been lucky to survive. But Memphis Belle II's pilot, Lieutenant James Parker, had attended a special briefing that Zuk had personally given to crews flying modified aircraft. Parker knew exactly what to do. He reached down to the cockpit floor where 3 manual valve handles were mounted within easy reach, clearly labeled with yellow paint. He rotated all 3 handles 90 degrees clockwise, just like Zuk had demonstrated. The backup hydraulic system activated. The monitoring equipment recorded pressure climbing from 0 to 1,275 psi over the course of 8 seconds. Not the full 1,500 psi of the primary system, but well within operational range. More than enough. Memphis Belle II stayed in formation, completed the bomb run, flew home to England, and landed at Bassingbourn on its own landing gear while ground-based engineers watched their monitoring equipment in real time and witnessed something that should not have been possible. A hydraulic system surviving a catastrophic failure and continuing to function. Robert Carlson, the Boeing engineer who'd spent an hour explaining why these modifications violated fundamental principles, watched the data playback in the debriefing room. The strip chart recordings didn't lie. The numbers were there in black ink on white paper, showing exactly what had happened at each moment of the mission. He stood there for a long time, just staring at the data. Finally, he turned to Major Watkins and said something that probably hurt to admit. This shouldn't work. The pressure dynamics are all wrong according to our design models. The flow rates are inadequate base.